Hello students, now we'll be studying about hysteresis curve, or you can also say hysteresis cycle. What is hysteresis cycle? It is generally a graph between internal magnetic field and external magnetic. Internal magnetic field is a magnetic field that is produced inside any substance due to the magnetic dipole that is created inside that material. We have seen that in paramagnetic material as well as ferromagnetic material. Okay, but here we will be talking only about the ferromagnetic material. This hysteresis curve is observed only in ferromagnetic substances. Okay, so this curve is relation between M and H, that is internal magnetic field and the external magnetic field, or in the NCERT textbook it is also given as B versus H, that is the net magnetic field, that is addition of internal magnetic field and external magnetic field, versus H, that is external magnetic field that is applied. So it shows that the relation between, what is the relation between M and H, and here it is observed that the relation is not linear. Otherwise what we had done, that M is directly proportional to H. This was the linear condition, but in this case it is not linear. For ferromagnetic material this is not linear. So what we'll do, and it mainly depends on history. It depends on history. You will understand this line at the end of this lecture. When we'll end the lecture, at that time you will get the meaning of this, that it depends on history. So what we'll do, we'll take a ferromagnetic material. It is generally unmagnetized material when it is in a normal form. A ferromagnetic material, what we'll do, we'll put it in a solenoid. Okay, we'll take a ferromagnetic material, keep it inside the solenoid, and then what we'll do, we'll apply the current to the solenoid, which means that when we are applying current to the solenoid acts as a external magnetic field. Solenoid will act as external magnetic field. Due to that, what will happen inside the ferromagnetic material? The ferromagnetic material will also start behaving as a magnetic material. So first of all, we'll start to draw the graph. The graph is M versus H. Okay, this is a positive direction, this is negative, this is also negative direction. At this point we'll say 0. Okay, so initially at 0 point everything will be 0, means if there is no external field, that is H is equals to 0 initially, at that time there is no magnetic field inside the material also, which means that M is also equals to 0. That is at this point, at point O or at point 0 everything is 0, that is H is also 0 and M is also 0. Now if we start and pass the current through a solenoid, it will start acting as a magnet. Okay, and if that acts as a magnet, what will happen? The material, ferromagnetic material that is inside the solenoid will also start to behave as a magnet, because the domain will align itself in the direction of magnetic field. So as we increase H, what will happen? We'll observe that M also increases. As we increase the value of H, M also increases. But at certain point, say A, at certain point A, if you go on increasing the value of H, the value of M remains constant. What does that mean? That suppose I am applying some external field on a ferromagnetic material, up till which point it will have the limit, until and unless all the dipoles are aligned in same direction. Till that point only it can act as a magnetism, or it can increase its magnetism, that is internal magnetism. Once each and every atom is aligned, or each and every dipole is aligned in same direction, if I go on increasing the magnetic field, external magnetic field, it will have no effect on the internal magnetic field, because already all the magnetic dipoles are aligned in a single direction. So this point is known as saturation point. This point is known as saturation point. Saturation point. Beyond this, there will be no change in the internal magnetic. Even though I increase the value of H, the value of M will remain constant. Okay, I hope this much is very clear to you. Now what we'll do, now if we start on decreasing H, if we start decreasing the value of H, that is if we decrease the current, ultimately the external magnetic field will decrease. So it was observed experimentally that when the value of H was decreased, or reversed, when the value of H was decreased, the magnetic field also decreased. But when the value of H became 0, the value of internal magnetic field did not become 0. That is, value of m did not become 0. So what happened in this? That some dipoles were still aligning in the same direction. Some dipoles were still aligning in the direction of magnetic field even though we have stopped the current or we have removed the external field, which means that ferromagnetic material will possess some kind of magnetism inside it even though the external field is removed. So this point is known as retentivity. This point is known as this distance. Suppose you name it as point B. So OB is known as point of retentivity, or it is retentivity. It is the tendency to retain magnetism even when the external field is removed. It is the tendency to retain magnetism even though the external field is removed, which means that if H is 0, M is still not equal to 0. So what shall we do to bring this on 0? What we need to do? We need to again disalign the atomic dipole, that are the domains. So what we'll do? We'll start applying the magnetic field, or we'll change the direction of current. So we'll apply the external field in the opposite direction. So what it will do? It will try to disengage the previous dipoles that were in one direction. It will get in the other direction. So what we do? We apply the negative magnetic field. So due to this, what will happen? At some point of time, the magnetic field inside the material will become 0. Let us say name this as C. So this point is known as, this is point C, and this distance is known as coercivity. Coercivity, which means that amount of negative magnetic field required, or the negative H required to get M equals to 0. To get M equals to 0, that is internal magnetic field. To make the internal magnetic field 0, we need to apply the current in opposite direction. Okay. So now from here again, if we continue to apply the current in negative direction, so what we'll do? We'll again repeat this procedure but in negative direction. So what we do from here? We continue to apply current in negative direction. So what will happen? There will come once again a point at which the current, the internal magnetism becomes saturated. Now the magnetism is saturated in this point. All the magnetic or the atomic dipoles in the magnet or ferromagnetic material are aligned in this direction. That is in negative direction, or you can say opposite direction. And once all are aligned, if I increase the external magnetic field in this direction, then also it will have no effect on the material, which means that this will act as a saturation point in reverse direction. Suppose I name it as point D. Okay. So from here what I will do? I will once again reverse the cycle. If I go on decreasing once again the current or current in solenoid, which means that decreasing the external field, what it will do? It will once again start reversing. Once again it will start reversing. Once again here I will get the point of retentivity, which means that H is 0 but relatively M is not equal to 0. This will be my retentivity in the negative direction. So once again, if I again apply the thing in the positive direction, the current in the positive direction, what will happen? It will try to align the dipoles in previous direction. It will try to align the dipoles in previous direction. At this point we will get once again the 0. Once again we will get magnetic field that is equals to 0, and if we keep on increasing it will come to the point A, which means that it will complete the loop. So from here if we start, what happens in the initial thing? We try to magnetize the material. We magnetize the material. We magnetize the material. Then what we did? Then we demagnetized it. Demagnetize it. Then what we did? We demagnetize it, means the magnetic field should be 0. Internal magnetic field is 0. Then what we did? We magnetized it in negative direction or in opposite direction. So from here we again magnetized it. Magnetize in negative direction, or you can say opposite direction, whatever, both are correct. Again from here what we did? We again demagnetize it, means again we make the material to lose its property of magnetism. Means here again it is demagnetization. Demagnetization. Again from here demagnetization, we again magnetized it. So the cycle is complete, which means this makes a loop. So what are the important conclusions from it? The important conclusion is, for a unique value of H, you will not get a unique value of M. Suppose if I take a point here, if I have value of h at this point, it will have, or suppose let me instead of this, I can take here, I'll take here so that we can understand it in a better way. So for this point, what will the value of, if I ask you what is the value of m for value of h, then I cannot say that there is a unique value of h, but there will be value of h at 3 points. One is at this, one is at this, and one is at this. There will be 3 value, 1, 2 and 3, that will be in straight line with h, which means that for unique value of h, I'll get 3 values of m. For any unique, you can do it in negative direction also. For any unique value of h, you will have multiple values of m. So on what does that m depend? It depends on the history. What is the history? That in which direction it was moving. It depends on the direction it was moving. For suppose if you want to find that what is the magnetic field, here you will get this value only if you know that it was traveling in this direction. If it would have been traveling in this direction, then you will get this magnetic field, this value of h. So it is said that it depends on the history. The value of m, that is internal magnetic field, for any given external field, the value of internal magnetic field depends on the history or from where it has moved towards which direction. Okay, I hope this much is very clear to you. And last and important thing, what is the meaning of hysteresis? Many will think that hysteresis is a word due to the thing history, but it is not actually due to history. Hysteresis means lagging, that is which leaves behind. Okay, so what is lagging? M is lagging to h. Whenever h is moved, what does m do? M tries to follows it, or m remains behind it. Means m is always lagging h, that is internal magnetic field is always lagging external magnetic field. I hope this much is very clear to you, and the hysteresis curve is also very clear. So in hysteresis curve, from where we started, we again reach the same point, which means it makes a loop. So generally it is also known as hysteresis loop also. You will be studying about it, studying about different hysteresis cycle in your future classes also, or in your further studies also. So this is the first type of hysteresis cycle that you are studying about it. I hope it is very clear to you. Thank you. Have a nice day. Keep studying.